Before the computer can be used to solve a problem, every step must be carefully planned in advance by the computer programmer. Programmers often use flowcharts to plan the various steps or procedures that the computer must perform. When flowcharts are used to describe computer procedures, each block is written to indicate a sequence of elementary computer operations. Each operation in the flowchart must then be converted to one or more instructions that the computer can recognize. Organized sequences of instructions make up a computer program. Each instruction in the program directs the computer to perform an individual task or operation when the instruction is executed. Most computers are designed to execute their own unique set of instructions. Consequently, an instruction set that can be executed by one computer will generally not work on a different computer. In this study unit, we're going to discuss the role of instruction sets. Our discussion will be divided into 3 lessons. We will begin by describing typical instruction formats. Then, in the next lesson, we will discuss various methods of addressing data stored in memory. In our 3rd and final lesson, we will define a typical instruction set and will write some simple programs using these instructions. Now let's begin our discussion of instruction formats. Instruction formats generally conform to the computer word size. Thus, if our computer uses a 12-bit word, each instruction is also 12 bits in length. Most instruction words can be broken down into 2 major elements, or fields, an operation field and an operand field. The operation field holds an operation code, or opcode as programmers usually call it. This binary opcode tells the computer what operation to perform, such as add or store. The operand field then tells the computer where to find the data or operand that is to be processed. Thus, an operand is simply an item of data to be acted upon by an instruction, and the operand field is a part of the instruction word that usually holds the memory address of the operand. For example, before this add instruction can be executed, the computer must obtain the operands to be added together. If these operands are stored in memory, the computer must be given the memory address of each. This is the purpose of the operand field. It directs the computer to the memory locations containing the operands that are to be processed. As we noted earlier in this lesson, the computer is designed to execute a specific set of instructions. Each instruction in the set has its own unique binary opcode. In this example, opcode 001 designates an add instruction, while opcode 011 designates a store instruction. A special circuit contained in the central processor decodes each of these binary opcodes and directs other parts of the computer to execute the instruction. For example, our computer performs an addition whenever it decodes an opcode of 001. Although binary opcodes are essential for the computer, they are very cumbersome for the programmer to work with. Therefore, to simplify the programming task, computer programmers use a 3- or 4-letter abbreviation that identifies each instruction. This abbreviation is called a mnemonic. Since mnemonics suggest the meaning of each instruction, they are much easier for the programmer to remember and to work with. The mnemonics, however, must still be converted into their equivalent binary opcodes before the computer can use them. Now let's return to our instruction format. Instruction formats used in some of the larger computers may contain as many as 3 separate operand fields. On the other hand, some instructions may not contain any operand field. The number of fields depends on several factors, such as the computer design, word size, and the operation called for by the instruction. Here's an example of an instruction format with 3 operand fields. Octal addresses 100 and 200 designate the memory locations of the operands that are to be added together. Once this addition is performed, the resulting sum is stored in a third location. Instructions containing 3 operand fields are not practical for most computers. This is because most computers are not designed with a large enough word size to accommodate many fields. Several computers, including some minicomputers, use just 2 operand fields. With these 2 fields, our add instruction can still reference 2 operands stored in memory. However, when only 2 operand fields are used, the resulting sum is usually stored in a location that formerly held one of the operands. In many digital computers, the instruction format is further simplified by eliminating still another operand field. This format is very common in minicomputers because their smaller word sizes, typically in the 12 to 16-bit range, cannot accommodate more than 1 operand field. Since single operand instruction formats can reference just 1 memory location, how is it possible to perform arithmetic operations which require 2 operands? This is usually accomplished by placing one of the operands in a special storage area called an accumulator. This accumulator, or AC, is part of the central processor. Consequently, there's no need to address one of the operands via the operand field. It's already available in the processor's accumulator. Let's return to our add instruction to illustrate how the accumulator is used. We've reduced the add instruction to a single operand field. When the computer executes this add instruction, it first retrieves or accesses the operand stored in memory location 100. Next, it adds that operand to the contents of the accumulator. The resulting sum is then held in the accumulator where it is available for further processing. Thus, an instruction with 1 operand field references just 1 memory location. If a second operand is required, such as in an add operation, the operand is stored in the accumulator, or AC. Up to this point, we've discussed in detail instruction formats containing anywhere from 1 to 3 operand fields. However, as mentioned earlier, certain types of instructions do not require any operand field, since they operate only on the contents of the accumulator. For example, prior to performing an arithmetic operation, it's often necessary to clear the contents of the accumulator to all zeros. To accomplish this, a clear accumulator instruction is usually provided as part of the instruction set. Other instructions may also be provided to increment or add a binary 1 to the contents of the accumulator, or to complement a number held in the accumulator. This means that each binary 1 is inverted to a 0, and each binary 0 is inverted to a 1. As we've just seen, these instructions have one thing in common. They operate only on the contents of the accumulator. Because these instructions do not address an operand stored outside the central processor, they do not require an operand field. The operand always resides in the accumulator. Let's summarize the 4 different instruction formats we've discussed in this lesson. Instructions with 3 operand fields can address 2 operands stored in memory and can also specify the storage address for the result. However, this instruction format is not widely used because it requires computers with large word sizes. Instructions with 2 operand fields are used in some minicomputers. This format can address 2 operands stored in memory. However, the result is stored in the same location that formerly held one of the operands. Instructions with a single operand field reference just 1 memory location. If another operand is required, it must be brought into the accumulator using a separate operation. And finally, instructions such as clear accumulator or increment accumulator do not require an operand field. because they operate directly on an operand stored in the accumulator. This concludes our discussion of instruction formats. Before going on to the next lesson, go to your workbook for review material and exercises on instruction formats. The workbook will tell you when to return to this program. In this lesson, we will explain some of the more common methods of addressing operands stored in memory. The most common method is to place the operand storage address directly in the instruction word. Because the operand field points directly to the location of the operand, this method is called direct addressing. The maximum number of memory locations that can be directly addressed is equal to the number 2 raised to the nth power. The letter n is the number of bits contained in the operand field. For example, if our operand field is 9 bits long, then a maximum of 512 storage locations can be addressed. In other words, q raised to the 9th power yields 512 possible addresses. Since most computers contain at least 4K of memory, to directly address all 4,096 locations, an operand field of 12 bits is required. In a typical minicomputer, the word size is limited to 12 or 16 bits. But not all of these bits are available for addressing operands, because some instruction bits must be set aside for the opcode. For example, suppose our minicomputer uses a 12-bit word and contains 4K of memory. If 3 bits are required for the opcode, then only 9 bits are available in the operand field for addressing operands. With 9 bits in the operand field, our minicomputer can address only 512 memory locations out of a possible 4,096. How can we modify our instruction format so that the computer can address all 4,096 memory locations? One of the simplest solutions is to use more than one word to hold all of the information contained in the instruction. In this example, we've divided the instruction into 2 words. One word holds the opcode, the other the operand field. This multiple word instruction solves our problem by providing enough address bits to address all 4K of memory directly. If our instruction references 2 operands, then 3 separate words could be used. The first word for the opcode, the second and third words for the 2 operand fields. When this 3-word instruction is stored in memory, it's placed in consecutive memory locations. Notice that to retrieve the complete instruction, memory must be accessed 3 times, once for each word in the instruction. This is a major disadvantage of multiple word instructions. Let's examine another possible solution to our addressing problem. In some computers, memory addresses are held in special locations in the central processor called registers. Let's see how these registers are used for addressing operands. Before the add instruction is executed, the operands must be retrieved from memory. The memory addresses of the 2 operands are held in registers R0 and R1, so that the registers point to the memory locations containing the operands. Thus, operands stored in memory can be addressed using registers that are part of the central processor. Because each register holds 1 complete word, it can usually accommodate enough address bits to directly address any memory location. Sometimes these registers are used for other functions besides addressing operands. For example, the registers may also be used as accumulators. This allows the central processor to operate directly on data without accessing memory. When these registers are used as accumulators, the processor could be directed to increment an operand held in one of the registers, or to add the operand in one register to a second operand in another register. The sum is usually retained in the second register. When these registers are used for other functions in addition to addressing, they are called general-purpose registers, or GPRs. This is an example of an increment instruction that is used in combination with a general-purpose register. The instruction breaks down into three major fields: an opcode or mnemonic, a mode field, and a register field. The register field tells the computer which general-purpose register is to be used with this instruction. In our example, it is register R3. The mode field then specifies how register R3 is to be used. For example, a 0 in the mode field indicates that R3 contains the operand that is to be implemented. On the other hand, a 1 in the mode field indicates that register R3 contains the memory address of the operand. Up to this point, we have discussed two solutions for our addressing problem. We can use multiple word instructions to increase the size of the operand field, or we can use general-purpose registers to point to the memory locations of the operands. Another alternative is to divide memory into smaller, more easily addressable segments that are called pages. In this example, we've divided 4K of memory into 32 pages. Each page, in turn, contains 128 storage locations. The page size is based on the number of address bits available in the operand field. In this example, 7 address bits are available. Therefore, we can accommodate a page size of 128 storage locations. In other words, with a 7-bit address, the computer can reference any location within a given page. But how does the computer know which of the 32 pages is being addressed? In some computers, a register points the computer to the starting address of the appropriate page. In our example, the register points to the starting address of page 1. The operand field in the instruction is then used to access a specific storage location within the selected page. Here we've addressed location 067 in page 1. In other computers, the instruction and the operand it is referencing are usually stored in the same page. This means that only a small portion of memory is easily accessible at any one time. Sometimes the instruction is stored in one page and its operand in a different page. When the instruction and the operand are stored in different pages, the operand is accessed by a method known as indirect addressing. With indirect addressing, the operand field does not point to the memory location containing the operand. Instead, the operand field points to a memory location where the address of the operand is stored. To access the operand for execution, the central processor must first retrieve the operand address from memory. Then the processor uses this address as operand. Thus, when indirect addressing is used, memory must be referenced at least twice, once to obtain the address of the operand, and then again to access the operand itself. How does the computer know when indirect addressing is being used? A special bit in the instruction word is usually reserved for this purpose. When the bit is set to a 1, it alerts the computer that indirect addressing is to be used to locate the operand for execution. On the other hand, when the bit is a 0, then direct addressing must be used. In this lesson, we've discussed two of the more common methods for addressing operands stored in memory. Examples of each addressing method are provided in your workbook. Therefore, refer to your workbook, study these examples, and complete the exercises. The workbook will tell you when to return to this program. In this lesson, we will define a typical instruction set and will explain how the instructions can be used to write some simple programs. A typical instruction set could include these 4 elementary instructions: clear accumulator, add, store, and halt. We will briefly define each one. The clear accumulator instruction causes the central processor to change the contents of its accumulator to all zeros. This instruction is often used at the beginning of a program to ensure that the accumulator contains all zeros before any computations are performed. In this course, we'll be using the mnemonic CLA to designate a clear accumulator instruction. Our second elementary instruction is add. The add instruction is made up of two elements, the mnemonic ADD and the operand field. The central processor executes this add instruction by retrieving the operand from the addressed memory location. Then it adds the operand to a value stored in the accumulator. The resulting sum replaces the value originally held in the accumulator, but the operand stored in memory does not change. A store instruction is also included as part of our instruction set. We will be using the mnemonic STR to designate the store instruction. This instruction causes the central processor to store the contents of the accumulator in a memory location specified by the operand field. But we must also have some way of stopping the computer. This is the purpose of the halt instruction, which we specify by the mnemonic HLT. Now that we've defined these four elementary instructions, let's see how they can be used in a simple computer program. Suppose we wish to develop a program to multiply 7 by 4 and then store the result in memory location 210. We'll begin by constructing a flowchart that lists the sequence of steps required to solve the problem. Our computer does not have a multiply instruction. Therefore, a series of 4 additions of 7 will be used to form the product of 7 times 4. In other words, 7 will be added 4 times to a location called sum. Before the first addition is performed, location sum must be cleared of any information held over from a previous operation. Therefore, we will include an initialization step to clear sum to 0. After the 4th addition, location sum contains the final result. We now store the contents of location sum in memory and stop all processing operations. Now that our flowchart is complete, let's convert it into a series of instructions that the computer can execute. The program must begin by clearing location sum. In this example, we will be using the accumulator as location sum. Therefore, a clear accumulator, or CLA instruction, is used to clear sum. The CLA instruction is followed by a series of 4 add instructions. The number 207 that accompanies each add instruction corresponds to the memory address of the operand 7. After the computer adds 7 to the accumulator 4 times, this store instruction transfers the final result from the accumulator to memory location 210. The last instruction in our program is halt. When the central processor retrieves this instruction, it simply stops all processing operations. The resulting program contains a total of 7 instructions. Note that we are using the same elementary instructions that were defined earlier. When this program is loaded into main memory, the instructions are stored in consecutive memory locations, starting at location 200. The computer will then execute these instructions one at a time in sequential order. Notice the halt instruction. It prevents the central processor from retrieving the contents of location 207, which in this case holds data, and decoding the data as an instruction. When this halt instruction is executed, the processing of our simple program stops. As we know, with more complex programs, the computer must frequently make simple decisions, choosing between 2 possible courses of action. For example, at some point in the program, a series of operations may have to be repeated over and over again. The computer remains in this program loop until a predefined condition has been satisfied. When this condition is met, the computer breaks out of the loop and resumes its normal instruction sequence. In other instances, a program may contain 2 or more separate paths. Again, the computer must decide which path to take, depending on whether or not a specified condition has been met. This process is called branching. Program loops and branches are implemented using a special category of instructions called program control instructions. The two most common forms of program control instructions are branches and skips. A branch instruction alters the normal program sequence by redirecting the computer to another point in the program. For example, this branch instruction causes the computer to retrieve its next instruction from memory location 201. By comparison, a skip instruction simply causes the computer to skip the next instruction in the program. Branch and skip instructions can be further broken down into conditional and unconditional. Conditional branch or skip instructions divert the computer from the normal program sequence only if a prescribed condition has been met. In this example, the computer will skip the next instruction if x equals 0. If the condition is not met, in other words, if x is not equal to 0, then the computer simply proceeds with the next instruction in the sequence. Conditional branch and skip instructions are easy to identify because we use the word if when describing their function. For example, skip if 0, branch if positive, branch if negative, and so on. Unconditional branch and skip instructions, on the other hand, always divert the computer's normal program sequence. There's no prescribed condition that must be met before the branch or skip operation can take place. Earlier in this lesson, we developed a program using these 4 basic instructions. Now let's add 2 program control instructions to our instruction set: a jump instruction and an increment and skip if 0 instruction. We will be using the mnemonics JMP and ISZ to represent these 2 new instructions. Our jump instruction causes the computer to branch unconditionally to another point in the program. In this example, the jump instruction tells the computer to retrieve its next instruction from memory location 300. Our other program control instruction is increment and skip if 0. As its name implies, this ISZ instruction causes the computer to perform 2 separate operations. First, the computer increments or adds 1 to the operand stored in a specific memory location. The address of this operand is contained in the operand field of the ISZ instruction. Then the computer tests the value that has just been incremented to see if it is a 0. If the value is a 0, the computer skips the next instruction in the sequence. On the other hand, if the tested value is not a 0, the computer ignores the conditional skip and continues with the next instruction in the sequence. Let's see how these 2 new program control instructions can be used to implement a program loop. Suppose this time that we're developing a program to multiply 7 by 11 and then store the result in memory. As in our previous example, we will form the partial sums in the accumulator. Therefore, we must first clear the AC of any previous information. We then use a program loop to add 7 to an accumulated sum until 11 additions, or loops, have been completed. A counter will be used to keep track of the number of program loops that have been executed. Initially, a value equivalent to a decimal minus 11 is placed in this counter. Each time the computer completes 1 pass through the loop, the negative count will be incremented by 1. The computer will then test the count to determine if it is 0. If the count is not 0, the computer will remain in this loop and perform another addition. After the 11th addition, the count is incremented to 0. At this point, the computer will drop out of the program loop, store the final sum in the designated memory location, and stop all processing operations. We are now ready to convert our flowchart into instructions that our computer can execute. The first instruction we write, CLA, clears the accumulator. An add instruction is then used to add 7 to sum. The operand 7, which is stored in location 207, is added to the contents of the accumulator. The updated sum is then held in the accumulator. After this addition, an ISZ instruction is used to increment the count stored in memory location 206. The ISZ instruction also tests the count that is stored in memory location 206. If the incremented count is not 0, this unconditional jump instruction is used to return the computer to the beginning of the program loop. On the 11th pass through this loop, the ISZ instruction will increment the count to 0. Consequently, when the count is tested for 0, the computer will skip the jump instruction and execute the store instruction. The store instruction causes the final sum to be transferred from the accumulator to memory location 210. Processing operations will then be terminated by a halt instruction. In summary, we have developed a program that causes the computer to multiply two values by executing a program loop. When this program is placed in memory, it's stored in consecutive memory locations. The first 6 locations hold the instructions. The next 3 locations contain the operands. In this lesson, we have developed 2 examples of programs that can be executed by our computer. These programs are included in your workbook for further reference. Additional programming examples are also provided in the workbook. This concludes the audiovisual portion of this study unit. Go to your workbook for review material, program examples, and exercises on the use of typical instruction sets.